To everyone. I, Dr. Neerav Pandya, warmly welcome to all of you on behalf of Applied Science and Humanities Department of Parul University, Vadodara. I also warmly welcome to our today's speaker, Dr. Som Narayan sir. First of all, I would like to introduce our today's speaker, Dr. Som Narayan sir. Sir has completed his PhD in physics with the specialization of condensed matter theory from MS University of Baroda. Sir has total more than 5 years research experience and he has published 27 research publications in peer-reviewed national or international journals along with 7 conference papers published in proceedings. During his professional career, he has completed 2 major projects funded by DST and UGC, and he has also worked with the BRC scientists as a part of his project work. He has been also awarded as gold medalist in BSc Physics from MS University of Baroda. Presently, he is working as a research scholar at Faculty of Material Science and Engineering, Warsaw University of Technology, Poland. So now once again, I warmly welcome you, sir, and I request you to start the today's session. Thank you so much.
Thank you very much, Dr. Pandya, for introduction. So, as introduced by Dr. Pandya, I'm Som from the. I hope the screen is visible to you. So, yes, Faculty of Material Science, Engineering, Warsaw University of Technology. So today I'm going to talk about the computational framework for the property prediction of the material. So good afternoon, everybody, and I'm hoping that all are doing well. So today, so starting with this, I will point out that today computational simulation plays an important role in the pandemic situation also. So computational framework for the property prediction of the materials is very much essential for today's day-to-day life. So why it is necessary and why we should choose the proper methods for predicting the prediction of materials and also in the bioinformatic fields. So I will start with, and I'm also very much thankful to Parul University to give me such opportunity to present my sum of work over here. So I will start with this. So the outline of the presentation is the choice of software and methods and which system for which software should we opt. And so there are basically 2 kind of simulation methods. One is called as a molecular mechanical approach and another one is a quantum mechanical approach. So I will bifurcate what is the molecular mechanical approach and quantum mechanical approach. So what are the advantages and disadvantages of mechanical approach and their common task we can do from mechanical, that is molecular mechanical approach. And recent works with the density function theory, that is a part of my PhD work also. So I will be doing these things. So why it is necessary to choice of methodology? So simulation is one of the boon for us to predict the materials and we can have the interaction between, we can know the interaction between the materials and their properties also. So from here we can see a graph of time scale and length. So length scale means what? As increasing the number of atoms, as we know that Schrodinger equation is there, that we can have the energy from the Schrodinger equation and the other properties also. But the drawback of that Schrodinger equation is that we can solve it up to a few number of atoms, that is hydrogen or up to helium. So density function theory and all this molecular mechanical approach or molecular dynamics is very much useful to have the properties of this material. So if your system is of 100 atoms or something near less than 100 atoms, so density function theory is a very much useful and which falls under the physics, right? And as we goes for the molecules, that chemistry comes into the pictures, and for that the number of molecules is more than 100 atoms, then we have to go for molecular dynamics instead of density function theory, as density function theory is much complicated and much complex to get the means it is giving the accurate result. I will describe about the density function theory also in molecular dynamics. So this is the picture where molecular dynamics comes into the existence when we go for higher number of atoms. The similar way, if we goes for more than 1,000 atoms, then material science they came into the picture. We describe about the macromolecules and all their properties with the help of molecular accelerated molecular dynamics or Monte Carlo or dislocation dynamics. So as we go for the engineering, for example, we go for the macro scale, so we can design the materials for the vehicles also and some bigger machines also. So that can be done by the finite elements simulation. So this is the basically the different simulation procedures you used as per the system. So over here it is the summarizations. If we go for the 1,000 atoms, or we can do electronic structure, that is the electronic structure, molecular dynamics, then accelerated molecular dynamics and dissolution. And that falls in the basically physics, chemistry, and material science. As we go for the engineering system, that is more than 10 to the power 8 atoms, then we go for the kinetic Monte Carlo or phase mold model. Or if we go for beyond 10 to the 23 atoms, then finite element simulation is better. So in nutshell, we can summarize like this. So if we want to have the exact solution of a system, then we can do only for the hydrogen atom by using the Schrodinger equation. Then if we increase the large number of the systems, complexity increases. But as we go for large number of atom, the complexity of calculation is also increasing. So we have to pay price. Means if we use quantum mechanical approach for getting the accurate results, we have to pay higher price. Higher price mean the sense of that is the time and computational cost. So that is so several approaches are there. There no mathematical solution are available for that. That is too much computational demanding, and it can be used for specific of the system. So specificity of the system. So coming to the molecular mechanical approach, so we can consider as a two balls with attached with a spring, and we know that we can use the Newtonian mechanics that F is equal to minus kx. Okay, so with that we can have the interaction between two molecules or two atoms. So it is very much good for the very big system, but sometimes results are not so much reliable, as we need to give more parameters to describe properly describe the system, then we get the accurate result. So what are the that parameters I'm talking about? So the parameters that we are talking about is called as a force field. So force field is basically it is of two type of that force field. We can give that force potential energy in the form of bonded interaction intramolecular only, that is the in between the molecules that bond, then energy of bonds, then their energy angle energies, then their dihedral energies, and non-bonded interaction intermolecular forces, that is bondable electrostatic energy and polarization. So with this, the more the accurate your force field method, the more the accurate result you will get. So with this, we can use molecular mechanical approach for the bigger system, for example protein or some molecules which is of 10 to the power 8 atoms or more than that. So explore what are the potential energy we are doing. So we are initially confine them in the using the periodic boundary conditions. So we can have that initial crystal structures and their force field, and we can have their hypersurface of energy. So in this case, as in case of the quantum mechanical approach, we can have the local minima, and in the case of this we can't achieve the global minima in case of molecular approach. So we can over here confirm that from the molecular mechanics approach, you are not able to get the local minima of system, that is ground state of the system. So you have many global minimums that can be used for further equilibration for there to have the ground state. So what we get from the explore of the potential surface energy, so we can have the minimum of the total energy corresponding to the conformers, whatever the single organic molecule is there or protein is there, right? Then polymers of a solids, that is SiO2 or TiO2, their adjacent sites on the surface. So they and from, as I said earlier, that approach is there is no general mathematical approach is used, so we can find global minima, and we cannot find the global minima, but we can have the local minima, and from the approach we can have the properties of this particular material we are interested. So what are the methods that from that we get energy minimization, right? What is the energy minimization? So we know that any system is stable when its energy is minimized. So energy minimization is the one of the method. Then there are statistical dynamics method and Monte Carlo if it goes beyond the 10 to the power 23 atoms. So with this, so molecular mechanics, what are the basic their advantages and advantages? So it use ball and spring description of molecules, and we are able to compute their relative strain energy, and as it's only able to get the interaction energies or their total energy of the system, so it is a cheaper as compared to quantum mechanical approach. Then it has a lost of empirical parameters that I have told earlier, that force field. So more the accurate you have the force field, the more the accurate result you will have, and that should be carefully tested or calibrated, or you can have from the literature survey also. So equilibrium geometries you can get. What are the disadvantage of molecular mechanical approach? Yes, it is not a quantum mechanical approach, so we will not able to have the no electronic interaction into the account. So no information on reactivity, cannot readily handle the reaction. So we can't predict the whether the bondings are breaking or bondings are making. Okay. So with this, we come to the know what is the molecular mechanical approach and how it is useful and what are their major disadvantages. So what are the common tasks we can do from the molecular mechanical approaches? That we can sampling the conformation spaces, so we can have structure and their dynamics, how they can do the interact with the other materials. So with this, we can have the energy calculation, then their structure refinements based on NMR data from the RSAB protein database, or you can get the molecules, or we can create our own molecules with their basic chemistry fundamentals. So then reaction path, then molecular interactions, and their we can indicate their mutation also. So many things can be done. The majorly it is done over here, and with this, there are a lot of open source softwares are available. So Ember and some of are often licensed versions also. So there are Ember, Charm, then GMD is also a visual molecular dynamics, but we can calculate some properties from it. Then Moldy, then Gromax, then Gomos, then macromolecules, and all these things. So basically, I'm working with the Gromax, and I'm talking about some of the things. So what are the steps for the doing the any molecular mechanical approach? So first of all, if you are planning to do some biological work or some protein based or some molecule based, so what you need to do, have the structure. So we can download a structure from the PDB file from CRSB. PDB means any protein database you can use to get the protein data structure. So it has a molecular structure based on the XRD database. So from the XRD or NMR database, you can have the morphology of your protein. So protein or some molecules, you can create it molecules on some PubChem or some sites you will use to have your interested systems. Then you have from the whole system, you can select the particular interested protein chain, or what you want to know the interaction between, what kind of change you want, what kind of protein system you want to have, that you can get from the PDB file. Then we need to, as we know that the protein and all these things are available in the solvation. So we define a box, then we put solvation with water, and some charges are over there on the protein, but we know that protein life has no charge, so we have to neutralize the protein chain. So after doing the neutralization and all these things, we need to do the minimization configuration. So what we have to do energy minimization. So after the energy minimization, so potential energies will be negative, and maximum force we calculated it's up to the 10,000 kilojoule per mole. So from here we can see that after 0 picosecond to we are going from 600 picoseconds. So 400 to 600 picoseconds, the energy is almost converged, and it shows that that minimization of that molecule is done. So with that, we confirm that minimization is there. But as we have included the solvation and all the ions for neutralization, so we need to have two type of equilibration that can be done from two ensembles, that is the NVT and NPT. So over here we control the temperature. So we can see over here the temperature is nearly 300 Kelvin as we go for 100 picoseconds. So you can do for more than 100 picoseconds also. And NPT, so pressure is nearly of 200 bar. So with that, we come to the conclusion that this system is equilibrate and it is a stable. Then we go for the MD production. So after that MD production, we can do the interaction which we can do docking, and other softwares are available for interacting the some ligands with the particular proteins or something like that. So with this, I will start with the one of the most pandemic situation over is due to the COVID SARS-2. So this is the one of the paper where they used. So they have not used. They have not do the MD simulation, but instead they do what they take the XRD. XRD of this 6LU7, that is a protease of COVID SARS-CoV-2 protein structure. So I can show you the database where sorry. So basically, I am talking about this database. This is the RSB PDB database. So over here you can type 6LU7. So it is a crystal structure of COVID-19 main protease in complex with the inhibitor N3. So there is an inhibitor of N3. As I told you, download from over here. You can download the PDB format of it, and opening with some visualizers, VMD or Chimera or something, PyMol like that, and you can have that structure. So after getting that this file, you can remove this N3 inhibitors, and in this paper they have bind with the other ligands that is used as a vaccine, that is lutein, N3, then remdesivir, and you know that chloroquine is also used as one of the vaccine for controlling the SARS-CoV-19. So I'm hoping that you all stay at home and remain safe as it is in pandemic situation, and it is day by day increasing the cases. So what in this, how the simulation is useful to have that vaccine for this. So we know that this COVID-19 has three structures, that is spike, membrane, and envelope. So spike is the most important. That is the interacting with our lungs cells, ACE2, that is called as a. So it has a structure which binds with this AC2 of our lungs or some throat, and it's means it is get into the cell and affects our cell. So how we will stop this spikes? So we interact with we can interact with the different ligands, and it's attached to that spikes. So we can see over here. So there are different binding energy that is related to spikes. So we can see in the spike protein. So we can see luteolin is very much useful. Whereas for the protease, you can see that ribavirin is very much useful, and for the PL-Pro, P85 ligand is very much useful. So with this, we can have some simulation. We can use simulation for having the vaccination, but it is underdeveloped. It is not that much advanced right now. So many scientists and researchers are trying to get the accurate results. So I'm moving to my work that is based on the utilization of dope. So melamine is also one of the mixed with the milk. So in China also many infants are died due to the addition of melamine in milk. So detection of melamine is very much crucial in the milk products, but unfortunately, the detection is very much lesser in a case of milk. So we have to enhance. So we use the surface enhanced Raman spectroscopy over here to enhance the peak of melamine. So over here we used triangulin GQD with the sulfur and oxygen dope for the enhancement of melamine detection. So we calculate their homolumo, then that is energy band gap, then molecular electrostatic potential, and their molecular charges to enhance to understand the mechanism of surface enhanced Raman spectroscopy. So the adjacent energy is found to be more for the oxygen doped GQD as compared to sulfur dope. So we can see over here that you can see over here that the melamine exhibit intensity is increased as we go for melamine oxygen dope. So it is an enhancement factor is of 4.51, where in case of melamine SGQD, there is another intensity, means increased in the intensity, that is 1408 mode is enhanced as compared to the pristine one. So from this we conclude that the GQD is indeed an enhanced the Raman spectroscopy modes of melamine, and it is helpful for detecting the melamine. So moving to the another thing, that is a lactoferrin. Lactoferrin is found in the milk, so which is very much essential for transfer of ions. For example, it's transfer silver, zinc, Fe, and all these things. So we in this case, it is we have to analyze these things also, where they detect Ag at different sites, and we have compared with the results with their experimental results with our DFT results. So we have seen that there is a certainly peak enhancement in the Ag at certain position only. So from the molecular mechanical approach, we are not able to get where Ag molecule is interacting with which specific proteins. For example, it is aspartic, or whether it is aspartic, or whether it is glutamic, or whether it is cytine, or whether it is we called as histidine. So from the Raman spectroscopy, we can know where it is interacting. So in the case of we interact with that histidine, glutamic at Ag at near to the this CO position, and we found that there is an enhancement in these peaks, and which is we can see this is the pristine L means LFT, and over here we can see there is an increase in the intensity. So this intensity is well matched with this one, and so from this we conclude that this peak is due to the interaction with the interaction of glutamic acid with the Ag molecule. So we can conclude that Ag2 is due to the interaction. Ag2 is due to the interaction of glutamic acid. And similarly for aspartic, we are able to get this enhancement, and we get to know that Ag3 is interacting with aspartic acid. The similar way we go for analyzing another things, and we come to know that this peak this peak is available in the Ag cytine. In the case of cytine, it is more, whereas as we go from as it is interacting with the Ag cytine, this peak is vanished. So its intensity is much lesser as compared to the pristine one. So over here we can see that as we go from pristine to interacting with Ag, this peak is get disappear as it interacts with Ag. So that also compare that with the all the three Ag molecules are interacting with the citing. And in the similar way, there is an enhancement we can see in this case, enhancement in this peak. It is due to the interaction of Ag with the histidine. So you can see that molecular mechanical approach, and with together with the quantum mechanical approach, is very much useful to get some of the reason why we are getting this kind of Raman spectra is due to the interaction between the particular Ag molecule with the histidine or cytine or these ligands. So with this, I'm going to my PhD work, that is I'm basically doing the density function theory to understand the effect of strain, or the effect of many fundamental particle strain on electronic, mechanical, and dynamical properties of two-dimensional material. So in basically why we choose this topic. So we need to have some properties, the tuners that can change the properties of the material for the different applications. So we used density function theory for this purpose. And what are the basically the two-dimensional material? As we know that whenever two-dimensional material comes, graphene come into the picture. As in 2014, Andrew James and his PhD students obtain the single layer graphene from the score-step method, and they also get the Nobel Prize for it. So but basically the two-dimensional graphene has one of the major drawback, that is its semi-metal nature, so which are not quite useful for the optoelectronic properties. So at that time, the band opening is one of the hot topic. And we also in our masters also, we just go for different doping procedure for opening the band gap. So there are other two-dimensional materials beyond the graphene has been discovered after the successful discovery of graphene. So these are the axenes, then axanes, then amaxanes, then chalcogenides, and basically oxides. So I will discuss why we are motivating to do these things. So some of the other elements also. So the motivation behind that in the masters also, that in that time graphene is very much popular, and so we doped with the different doping with the nitrogen, and there is a band opening. So it is showing that layer interaction with the hexagonal boron nitride and graphene. So as we increasing the distance between the hexagonal boron nitride and the graphene, so there is a band gap of nearly about 2.4 angstrom. The band opening is there, but as we move for 4 angstrom, so there is no interaction between the hexagonal boron nitride and graphene. So we can have the semi-metal nature again. So with this, we just go for the nitrogen doping, and we found that with the nitrogen doping there's a band opening of 0.67 eV. So that motivates us to get them some modules or some methods to tune the electronic properties or some fundamental properties of materials. So we just go for the periodic table, and we found that the that is a P block elements such as antimony, bismuthine, and arsenide are known for their optoelectronic properties, and so they are not yet go for the 2D materials. So we took the opportunity and analyzed their 2D materials. Similar way that in the bulk form, zirconium family are known for their photocatalyst, water splitting for as a photocatalyst. So and other we go for there are many two-dimensional energy applications, and again the most important is that we can see day by day the two-dimensional materials based applications is increased, and it's still going on. So two-dimensional materials plays an important role in the mankind applications. So what are the approaches for the tuning the properties of two-dimensional materials? So we the first come to that two-dimensional material is a confinement in a dimension, that is it's from three-dimensional to you can confinement in one of the direction, then you will get two-dimensional. In the similar way, you go for 1D and quantum dot also. So if you confine all the three direction, you will have that quantum dot. So going for another one is a strain. So strain can be seen as a bending and stretching experimentally, and similar way there is another one to tuning the properties is doping or defect. So you can see over here we can dop. So I have sold nitrogen doping opens the band gap of graphene of 0.67 ev. So similar way there is a heterostructure. So if we put two layers together of two mono layers, then it forms a heterostructure. So there are two kind of heterostructure. One is a vertical heterostructure and another one. So there is a strain between the substrate and above layer. So we can minimize the strain between them by rotating it, and we can have the Moria pattern. And so there is another one. So even though in the heterostructure also, so there is a van der Waals interaction between two monolayers that can be tuned with the different atoms or molecules in between the heterostructures. So that increasing the distance between two monolayers or two heterostructures and enhanced or change their properties as compared to their heterostructure. So I will discuss about some of the methods. This approach is for tuning the optical properties or optical or electronic properties of two-dimensional material with their dynamical and mechanical properties also. So coming to the first is the water splitting method. What is the water splitting method? So as we know that water splitting method is a consist of the breaking of hydrogen and oxygen atoms from the H2O. So it is called as a HER, that is hydrogen evolution reaction, and another one is called as OER. So basically, by modeling, it is seen that the interaction between the catalyst and the catalytic surface and that HER means hydrogen or oxygen, that should not be more means it should not adsorb. It must bind it very strongly. So desorption process will be difficult, or if bind loosely, then the absorption process will be difficult. So there will be a optimal adsorption process, so that can be done from the Gibbs free energy, and the Gibbs free energy should be equal to 0 for having the better catalyst for hydrogen evolution reaction. So from that we from the literature survey we can have that adsorption energy should be of 0.24. So the adsorption energy, so Gibbs energy is 0, so adsorption energy should be equal to minus 0.24. And for OER, it is 0.33. And with this, we can calculate the adsorption energy. So there are two kind of catalysts, that is electrocatalyst, and another one is a photocatalyst. The one source is a electric bias, and another one is obviously solar photo means giving the. So over here we can see over here that one hydrogen is adsorbed on the surface, the another hydrogen will come, and it will take the another means these two hydrogen together, and it evolves as a hydrogen gas. So we in the nutshell we conclude that the optimal adsorption energy for the hydrogen and oxygen is of 0.24 ev and 0.33 ev for having the good catalyst. So we have analyzed two system, arsenine and zirconium system, as I showed. So what are the methodology? As I showed, it is a quantum mechanical approach. Density function theory is basically, it is a Schrodinger equation. It solves many body problem in terms of density. So instead of computing 3 and degree of freedoms, it's to deal only 3 degree of freedoms. That is the major breakthrough of density function theory. So we used effective potential is a combination of ionic Coulomb potential, classical Coulomb potential, and exchange correlation potential, which is very much as in case of molecular mechanical approach. The force field is very important in the similar case. The LDA and GGA, that is local density approximation and gradient general approximation. The higher the exchange correlation potential you used, so higher the accurate result you will get. So this is the another the methodology we use, density functional perturbation theory, for calculating the dynamical stabilities. Then van der Waals interactions also we have included with the that DFT are not able to include the van der Waals interaction. That can be done with the inclusion of dispersion correction D2 or D3. So and the optical properties are calculated using the random phase approximations, and you used Kramer-Kronig relations for that. And for elastic constant, we used elastic code, exciting code. So for getting the elastic, that use Hooke's law only, guys. So So coming to the results of the one of that is the hydrogen evolution reaction for the role of an arsenine as a nano shell. So we as we know that for photocatalyst, so that band gaps will be nearly near to the 1 to 2 eV. So it falls in that case, but it is has an indirect band nature. So we just see how it is going to be photo as a photocatalyst. So we absorb hydrogen and oxygen over it, and as we found that the binding energy, that is adsorption energy, it is going to be 1.27 and minus 2.85 ev respective for hydrogen evolution reaction and oxygen evolution reaction. So we can see over here that negative sign shows that it is a chemisorption, and it is a minus 1.27. So the desorption process will be difficult. So how we are going to use it as a photocatalyst? So we think of doping different dopants, so that can alter their fundamental band gap. So with that, we doped with the boron nitrogen, the nearby boron nitrogen oxygen. So by just doping boron, the band gap is decreases, and still nitrogen. So we can see over here that it shows the p-type semiconductor nature, where in GA also it shows p-type of semiconductor nature, where in case of arsenine, germanium, it shows an n-type of semiconductor nature. So with this, as this boron arsenine and boron nitrogen and gallium and germanium has a +3, you can say +3 or +2 as a for nitrogen, and boron is +3 oxygen state. So it shows the band gap is decreases. And as we go for arsenine and oxygen, due to their oxygen state -2 oxygen state, this shows a defect bands near the Fermi, and leads to the metallic nature. So coming to the adsorption of hydrogen and oxygen, we found that we absorb hydrogen at different positions, and on the basal plane we found that it enhances its property as a metallic catalyst is more useful for the hydrogen evolution reaction, and which is also found in the literature that metallic nature catalysts are good for, as platinum also metallic in nature, so it is good for the hydrogen evolution reaction. So we found that oxygen doped arsenine is good for the hydrogen evolution reaction, as its Gibbs free energy is nearly 0, whereas case of arsenine based boron doped arsenine source is good for the oxygen evolution reaction. So we can see over here the adsorption energy, the least adsorption energy is for O doped for hydrogen evolution reaction, and for oxygen doped it is boron doped arsenine. So with this we can see that tuning the properties of the material can be useful for the different application. And we just go for the another system, that is zirconium, Janus, and ZrS2 or ZrSe2. So we know that the ZrSe2 is used as a photocatalyst in a bulk also, but in case of 2-dimensional, it also exhibits the band gap of 1.58, which is in the range of 1 to 2 eV, that can be used as a photocatalyst. Whereas Janus is one of the layer is peel, and it is going to be of different systems. So over here, that one is of layer, one of chalcogenic layer is sulfur, and another one is a selenite. So we can see over there it exhibits intermediate properties as compared to their parents. So you can see over here ZrS2 exhibits band gap of 1.58 eV, whereas ZrSe2 exhibit 0.84 eV, whereas ZrSe is its band gap is 1.08 eV. So both can be used. ZrS2 and ZrSe2 can be used as a photocatalyst, whereas in case of ZrSe2 can be used as also as a photocatalyst. So we just go for this. This is a density of the states. So it's helpful to have the interaction. So if there is a distribution, this is the density states of hydrogen, and it's distributed all over. So it shows the interaction between the system and with their particularly hydrogen and oxygen atoms. So we can see over here when in case of ZrSe2, the density of state is much more as compared to these two. So it shows that the interaction between ZR Ac2 and hydrogen is lesser as compared to ZR ZRS2 and ZRSSA. So with this, we that confirm with their adjacent energy also, and we found that there are two edges. So instead of SH is more active towards the hydrogen as compared to SEH, and overall from the out of three systems, Janus is showing better result as compared to their parents. So that shows that the tuning is very much essential, and it is very much useful to have the better results as compared to the existing materials. So with this, we found that ZSH is very much useful for the hydrogen evolution. Still, it is not that much good as compared to the platinum. So we just go for the different dopants, platinum, tungsten, and niobium and B. So we found a similar result, but in this case, as we know that the band gap of ZrSa2 is 0.84. So after doping, it shows a metallic nature, and we found that NP doped ZrSa2 is a better catalyst for hydrogen evolution reaction. So indeed, the metallic catalysts are good for the hydrogen evolution reaction as compared to the semiconductor photocatalyst. So we conclude from that doping is indeed changes the fundamental properties of the material and can be used as a catalyst for hydrogen evolution reaction. So coming to the another thing, that is the bismuthine arsenide and bismuthine antimonide. So we go for the arsenine and all these things. So coming to the bismuthine exhibit a band gap of 0.61 eV. So for optoelectronic properties, the band gaps will be of 1 eV. So it can be used for other applications, spintronic or all applications, but for optoelectronic properties, we have to have the band gap of that of 1 eV. So what we basically think of that we make a alloy with the antimonide and arsenide. So as we know that as we moving upward, the semiconductor metallic nature is decreases. So we doped with the antimonide and antimonide. So we found that the band gap is increasing of 0.99 eV. So as we substitute 50% of we are making the alloy 50% of bismuthine and 50% of antimonide, so band gap is increased 0.99 eV. So similarly, we go for the arsenine, and we found that the band gap is going nearly to 1.11 eV. So as we can see that we moves from bismuthine to bismuthine antimonide and bismuthine arsenide, the band gap increases as we moving from the bismuthine to arsenide alloys. So with this shows that these material are very much useful for the optoelectronic property, particularly BISB and BIAS. So we have calculated the optoelectronic properties, then more of the regions are falls in the visible region. So that gives us that courage that this material are more useful for the optoelectronic properties. And with this, we just confirm their strain properties also. So we found that at a 3%, or we can see over here nearly of 2 or 3%, it shows a transition from direct to indirect, and then it's becomes a metallic. So with this we confirm the strain also. So if we use some substrates or something, and we prepared a device, so if the strain goes beyond 2% or 3% of strain, then it shows a metallic nature or indirect nature. So sometimes it happens that that means the variation in theoretical and experimental work is that due to the strain effect, there is a change in the property of the material, and due to that we don't get the actual properties that we predicted from the theoretical point. So we have to minimize the strain effect on the material, so we can use their inherent properties for optoelectronic properties. So with this, it goes direct to indirect metal. So if the strain increases beyond 3%, in the case of BIAS beyond 3%, its band gap still increasing from 1.17 eV, where for BISB it is 1.02, and for 5% it remains. But the nature changes; it changes from direct to indirect nature. So we have to look over it. So we just go for whether this alloy increase their dynamical stability or not. So we see that up to 10% of strain this material is stable for bismuthine. So as we go for antimonide or arsenide, so in case of arsenide we can see that it goes up to 20% of strain. So dynamical stability also increases with the alloying. So we can see, and in case of bismuthine it is a 50%. So as we move from the bismuthine to bismuthine arsenide alloys, their dynamical stability also increases up to 20%. So their dynamical stability and their mechanical properties also be found that increases with the alloying. So alloying is a very much useful for getting the stiffer material and having the accurate optical band gap to have for the optoelectronic application. So mechanically it is found to be 15% tensile strain can be makes it mechanically stable, and its Poisson ratio is also about 10% of the strain that beyond the it exhibits a exhaustive behavior as it is found in case of the graphene. So with this we have gone for the another is a system is a silicene. So silicene is also one of the falls under the family of graphene, having the semi-metal nature, but the thing is that silicene is not naturally found. We have to prepare it. So a lot of efforts has been dedicated to silicene, to having the proper substrate. So but the major is what that silicon oxide and all this distort the silicene, and the transition metals or metallic IRO2 and all this system makes it silicene metallic in nature. So we are in a search of some heterostructure or some substrate that can be used for the opening the band gap. Yes, band gap is increased of 0.01 EV or 0.05 EV with the use of GES and PTS2, but still it is not that much for optoelectronic properties or for the other applications. So we go for there's a P2S2 and the lattice mismatch of silicene and SnSe2 is of 0.18%, which is lesser. So we can use a lattice match model for preparing their heterostructure. Otherwise, we have to twist it, and we can make a Moria pattern to decrease the strain between them. That's also one of the reasons. So we used SnSe2 as its band gap is nearly 0.84. So silicene exhibits semi-metallic nature at we can see a Dirac point near the brilliant zone K, and as we move from SnSe2, its band gap is of 0.84 eV. So we just thinking of getting the semiconductor nature, but unfortunately the interaction between silicene and SnSe2 is much higher, and due to the interactions it shows a metallic nature. So over here we can see that blue color is for silicon and red color for SnSe2, and due to their strong interaction between them, there is a distance between them and decreases as compared to the after relaxation. The distance found to be 3.903 Armstrong. So with this, due to the strong interactions, there is a hybridization between SnSe2 and silicene. So we can see over here SEP and Si of silicene at silicene interact and gives it to be metallic nature. So we are thinking of intercollecting with the different atoms, chlorine, chlorine, as it is a yes, please.
Sorry, sir, to interrupt you. Sir, we have 10 minutes.
Okay, no issue. I will just finish it.
It's okay, sir, no problem.
Okay. I will conclude it with that. Okay. So okay, I will not going in depth of this thing, and I will just going through. So with the chlorine, so it is attached with the silicene, So that's also that due to the hybridization between chlorine and silicon, it gives us a metallic nature. So similarly, we and from the charge distribution also we found that there is a charge transfer from chlorine to silicon. The similar way we go for the phosphorus, and we found that it's still we are not getting the we are still getting the metallic nature, and there's no hope for getting semiconductor. But eventually we found that NH3 is so we use as an inert nature, so we put NH3 in a different two configuration, one near to the silicon nitrogen and hydrogen towards the silicon. So when we found that nitrogen towards the silicon, it's interact with the silicon and gives us a metallic nature. But where in case we get a hope, where in the case of hydrogen towards the silicon, so the distance between silicon and SnSe2 get increased, and that because their van der Waals interactions, and the charge transfer is also minimal in this case, and the band gap of 0.23 eV is achieved. And we can see over here that the charge transfer is lesser in case of so indeed intercalation also tunes the properties of the material. So at the last thing is the perovskite materials, which are known for the solar energy applications. We go for the three different configurations, that is the bulk, then 2D and 1D. So we found that the band gap is nearly of 2 eV, so it can be used as a solar cell devices, and two-dimensional material, the two-dimensional methyl ammonium lead iodide is used for solar cell application also. So we go for that, and we found that from the DOS it can be used as a PIN configuration, and we confirm it from the optical properties of MAP, is that over here we can see that JDOS, then joint density of state, which shows that 1D is poor for solar cell devices, but it can be used for diode or other applications. And the similar way 2D MAP shows laser JDOS, which shows that 2D MAP is even good for as compared to their bulk form. So we calculate the solar parameters with the two configuration, TiO2 and PCBM as a whole transfer electron and material. And with that we found that the highest efficiency we got for that two-dimensional material is 23.6 in the case of TiO2, which is also well matched with the other experimental works. And with this, we also applied a strain, and we found that about 4% of the strain, it shows the indirect nature, and the efficiency decreases as we apply the strain. So we also applied the strains and all these things, and we found that 2D MAPI is a best for the what we can say that photocatalyst as a photovoltaic cell, solar cell applications. So with these are the conclusion that that the band gap of 2D materials indeed with enhance with the doping and their catalytic activities enhance with the doping. In case of HER, metallic material is good. For OER, it is semiconductor is good. For group 5, it can goes for high mechanical strain and exhibit high mechanical strain, and can be used for photodetector sensor and photovoltaic application. Where in case of with the intercalation, the silicon heterostructure, we observed the band gap of 0.23 eV, and in this case of MAPI we observed 23. So I'm thanking you yeah, I'm thanking you for your attention. So thank you very much.
Thank you so much, sir, for a very informative session. I think you have covered a lot of information that what can be done using DFT. So that's a very nice presentation, sir. And there is one question from those viewers, those who are on the Facebook Live platform, that one has asked that what is GQD?
GQD is a graphene quantum dot.
Okay, sir.
It is a short form of sorry, I forgot to mention. GQD is a graphene quantum dot, and we used triangulin for the detecting the memory.
Okay, yeah. Sir. And sir, what about that? You just told about various software. There is one basic question. What about Ember and Charm? You told. about those two software?
Ember and Charm are Forcefield. They are softwares for creating the force field. So you can
Forcefield.
use the yes, and Ember is also software for it is used for calculating the means it is a molecular mechanical approach software for using. You can use it for it is like a Gromex only. So it is a software for calculating the protein and equilibrium energy and all these things. So you can calculate from it.
Okay, okay, sir. And sir, there is also one question from my side. Sir, you told about that protein for the related to COVID-19, and you told about that RCSB downloader, and that
Yes.
will be PDB format. So, which type of information we are going to get there from that in that PDB format? It will contain which
Okay,
type of
in the
information?
PDB, it is like there is a all proteins are there. So I will show you. So in that case, you just go display the file, PDB format, right? So in this case, this is hope you are seeing. So in
Yes.
this case, all the bond angles and bihedral and all these things what I told, that information is there. So in this sequence is there. So glutamic is there, glycine is there, cytosine is there. So all these chains are over there, and so it has all the information regarding their positions, their position, their charges, and all these things are given in the PDB files. So that is a basically just like an input file for the molecular mechanical approach that is converted into particular Gromex file or something like that.
Okay, sir. Okay, sir. Thank you, sir. Is there any question from the participant which are available here?
Okay, only one small question. You said okay, there are some proteins for uh, COVID-19. Can you suggest any good monolayer for biosensing of COVID-19 virus?
Okay, bio means it is like that. Okay, for sensing procedure, graphene and all materials are used. Graphene, then hexagonal boron nitride. So it is like that. You just have to have that some materials have band gap nearly one or two or is something like that 3 eV. So that the semiconductor materials basically you can say that semiconductor material are very much useful for sensing procedure. So and all other things are also there. So it's up to you which system you want to means it is like a predicting it first, and if it gives a result, that is it is like a you go for different we don't have that this is good and this is bad. So we are just going through all the system that looks that has a potential to be as a sensor, and you just calculate it and just see whether as it is says that simulation has this advantage that you go on trying and trying the one the better you get the result, that can be inspiring for the experimentalists to do experiment like that.
All right, thank you.
Okay. Thank you so much, sir. So now, due to time limitation, we are not going to move ahead for any questions. So once again, I am expressing my sincere gratitude for accepting our invitation and for giving very informative session for all of us. And thank you so much, sir, once again. And thanks to
Thank
all
you
the
very much. Thank you very
participants
much.
which are available here and those who are on the Facebook Live platform. Thank you all.
Thank you. Okay then. So I should leave.
Yes, sir, you can leave.
Thank you very much. Thank you very
Yeah,
much
thank
for
you.
giving the opportunity. Thank you. Thank you.
Thank you.